Life is complicated. Even our normal routines, like what to wear for the day, what to eat for dinner, are spoiled for choice. But life is simple. It's just that we insist on making it complicated, said by Confucius, one of the greatest Chinese philosophers. If I tell you today we can use mathematics to simplify our life, you may laugh it off. Oh, come on. Life is already complicated enough. We don't want you to bring more math to overcomplicate things. But that is a typical misunderstanding about, or stereotype about mathematics. So many of us have been put off by math because we think it's loads of logic and rules and numbers and equations to memorize. But math is not just about numbers and equations. It's also a way of thinking. And in this talk, I would like to share with you an example of how math as a way of thinking can actually help us to simplify things in our life. Some of you may guess right that a mathematician's favorite food is pie. So here we got 3 pies: cottage pie, shepherd's pie, and fisherman's pie. In a mathematician's eyes, these 3 pies are more or less the same. They just have different fillings underneath mashed potato topping. If you're going to ask them to write down your 3 recipes, first of all, they're going to write, okay, let's make the filling a variable, so can you insert your own preference of filling meat or fruit. Oh, hold on. You can also make the topping into another variable, so you can change the topping to anything you like. So now, there we go. You have a blueprint for all pies. You can even invent new pies. How great is that? That is how math works. Math tries to looking for things, similarity between things, so that you only need one recipe for so many different situations. The key thing here, when you ignore some details, the things become easier to understand. And that is the process of abstraction. Abstraction paved the way for the development of mathematics. And us humans actually are so good and with abstraction. It's actually hidden everywhere and in every aspect of our life. Currency is a type of abstraction for the objects of service you're going to pay. And the numbers also is abstraction for the objects in the world. The road sign is a form of abstraction for the information to tell the road users. Our human can learn to drive in under like 20 hours of driving lessons. We learn to use a phone and use a cash machine, maybe under a few seconds or minutes. The thing here is because abstraction hide away the implementation detail from us, expose only the functionality. So we don't need to know how it works, but we get to know how to use them. So you see, abstraction simplifies things, so it makes life so much easier. But not many people are so good at or so comfortable with abstraction because it's a limp from the reality. The difficulties about abstraction is often we need to translate between the abstract and the reality. A map is an abstraction to the reality. Some people find it really difficult to use a map because we need to link the map to the actual place we are actually running around. First, we need to work out where we are, and then we need to work out which way we are facing. But Google Map here gives a brilliant tool to solve this both for us. Math is the same here. We have to, first of all, from the reality, change to the reality to the abstract world, because we have to draw, someone has to draw the map in the first place. And then we do our logical reasoning inside the abstract world. And then finally, we have to turn back to the reality again. The key things here is being able to move back and forth between the abstract and the reality. But there are so many, in the math, there are so many different situations when we require different right amount of level of abstraction. For example, in the Google Map, do we need to know all the pictures of buildings where there is grass? It depends what you use the maps for. If you are driving, you care more about whether there is one-way system or whether there is a roundabout, how many exits there are. If you are on foot, it's not quite necessary. If you are taking the London Underground, you want to get from station A to B, you want to know which line you should take, which direction you should take. You don't care about the rest of the lines and the stations or things above ground. The same is here. The same is true for math. There are so many different levels of abstraction available for different applications. How we know which exactly level of abstraction is right for a particular situation? Your parents may ask you to tidy up your room because from their eyes it's quite messy. But you don't think so because you can find everything because they think that you are exactly in their place. But imagine if you're dealing with a huge warehouse with hundreds of thousands of items. You cannot scatter them around on the floor. You want to organize them into shelves, different shelves, and with a really organized way, so you can find things among this huge pile of stuff. But if you imagine, if you would keep adding things to that warehouse, the things are expanding at an exponential scale. How are you going to match that? How are you going to find a single thing among this huge amount of items? In the abstract world, we can expand this 3 dimension into 4th dimension, 5th dimension, 6th dimension, all the way above. So how we organize things in an abstract world, we can still find things in a really complicated world. But math doesn't need this kind of organization for over thousands of years. But as our civilization grew, math has been ever expanding and keep developing. So much so that even mathematicians themselves found it really difficult to understand most of the mathematical things. So they started to put more interest on their own area of interest. So you have topologists who study topology, you have statisticians who study statistics. And then they are starting to devote into their own area of expertise. They talk less and less to each other. They become siloed. It's until last century, 1940s, 2 mathematicians, they want to know what's the similarity or connection between 2 mathematical theory, algebra and topology. And then the study eventually led to a new branch of mathematical theory called algebraic topology. But at the same time, they found out that the way of studying can also be generalized to study all sorts of mathematical things, their relationships, their similarities, the structure of them. So this is how an abstract math called category theory was invented to organize principles inside the world of mathematical things. So it is another abstraction to the mathematical thing. So that's why it's called abstract math. But also because it studies the mathematics, that is why it's also called mathematics of mathematics. But how does an abstract math category theory works to organize mathematical things? You can see the pictures here, which are used to introduce category theory. No equations, no rules, just single dots and arrows and the structures of them. But that's the beauty of category theory. That's the beauty of abstraction. All sorts of mathematical things can actually be simplified into single dots. And how they're related, we're using arrows to present the relationship. And then group of things, how group of things are related to a group of things. Because things can be simplified into dots, so we can also simplify the relationships, the arrows, into dots. We can simplify different shapes of arrows into single dots. So up on the next level, we can analyze how relationships are connected with relationships. And on the other level, we can analyze what's the relationship between relationships or relationships, and so on and so forth. So you see, we can organize complicated mathematical thing into this kind of multi-level of abstraction. We can draw out the complicated principles on a single page. So maybe we can work out which part of math is easy and which part of math we will need in a particular situation. But it sounds still, some of you maybe find it really abstract. but how do we use this abstract math in our real world? As mathematicians will think, they're using this category theory to study mathematical things, to apply the category theory inside the world of mathematics. And they think the way of studying can help them clear thinking and understand the world around them. As an engineer and a non-mathematician, can we also harvest this organization for mathematical things and use it in our engineering domain, make our thinking more clearly, and harvest this clear thinking to simplify our complexity in our manufacturing world. So now let's move on to from the abstract world to the concrete world, a digital world, or more specifically, a digital world of manufacturing. You can imagine that this digital world is like hundreds of robots and machines working simultaneously and collaboratively to produce different items like cars, furniture, or processing food. And they are processing large amount of data in every second, store them, exchange them between different machines, need to analyze them, and output to human for human intervention. It's really complicated digital world, and also with the machines. And now, because we are into a new era of the fourth industrial revolution, the vision of this revolution is we want the machines the system become autonomous, in a sense like self-driving cars. So they know what to do without any human intervention. They know how to slow down at a corner, how to stop at a traffic light. They know how to avoid pedestrians. So that is what the autonomous manufacturing wants. So to make the machine decide what should do. It would be lovely to make a machine to do all these autonomous tasks. But that's not quite easy. Even teach the machine to do one single task, it requires we understand this one single thing in a totally different point of view. We know how to walk, right? We pick it up since you're maybe 1 year old. But if you're about to teach a machine to walk, you need to rethink, how did I walk? How to wave your arm? How to lean forward? What's the center of gravity? Which foot to take, and how to bend your knee? You need to rethink about that in a very single detail. You may know how to bake a cake, but you're about to make a machine to bake a cake. Every single details, you also need to take some careful thoughts. Even cracking an egg, let the machine do that cracking egg thing. How hard the machine should know to crack the egg without breaking the eggshell all over the place. But this figuring out of all the details to teach or to instruct the machine to do a task, every single details and every step, this is actually a process of creating an algorithm, which Ada Lovelace has figured out nearly 200 years ago, long before the computer was invented, which laid the foundation for the invention of computer. But from our today's standard, make a machine can make a cake. Isn't that clever? We have all sorts of machines like that. So what about make a machine which can invent a new recipe that can make a cake? It's a bit smarter, right? And we'll take it a bit further. What about make a machine that can make machines that can invent new recipes that can bake a cake? Isn't that even more intelligent? So you see, this is how each level up is a further level up of abstraction to the previous level, and this is how multi-level of abstraction can make machine smarter. But make machine smarter, or make machines to make machine, is so broad research topic that I can handle, or my team can handle. How are we going to approach this grand challenge? we can approach this grand challenge by building some foundation to working towards that. First of all, we know that the machines need to handle the multi-level of abstraction, but they barely even know how to abstract at first place. So we human, we have to help them to do that. So we used category theory, which is a multi-level abstraction language, for that foundation. So, okay, we found our foundation. Good. The next thing is we, as human, have to use a tool or platform to help us organize all sorts of things we want the machine to do on a multi-level of abstraction. Is there a tool available? So we did our research and we find, okay, not that yet. Because, first of all, category theory is a mathematical language. It serves to organize the mathematical things. Machine doesn't know a mathematical language. We have to find a way to let the machine understand what we want to do for the machine, on the machine. And we're looking for tools which can kind of, using category theory, and can do some stuff, organization stuff, but some of the tools are not served for our purpose in our engineering domain, or they serve for the mathematician's point of view. So no, we don't have this tool available. So that's a bit frustrating. So what do? So the things we want doesn't exist yet. We step up and make our own. So eventually, we ended up developing this tool by ourselves. To make this tool first, we have to design a language which don't require the engineer to learn all this complicated mathematical stuff. We want to make category theory make more appealing to engineers. So developing all this language is like building a basic set of digital Lego blocks. So this limited basic set of digital basic blocks can help us human or engineers to build any type of Lego models with multi-level, and we build a cat lab for the users to do that. And what you can do with this module, you can ask questions, you can play with them, and then the module will give you answers. How it does that is, imagine those Lego models are hollow inside, and the data inside of this structure are like spherical balls, which can move forward or backwards, depending on what structure it is. And then the question you're asking the module actually push the ball forwards. And the final answer might be where the ball ends at the end, or which route or routes it takes to get there, and how it behaved throughout the whole journey. And yeah, it's good to get to play and build a model and get to play with them. But you might ask how we get to use these Lego models for. This Lego model, we can think of like giving the machine a little bit common sense of what is happening, what the world is, building a world model for the machines. So to know how this world works will eventually lead them to plan better and predict better for the future and make the right decision at the right time. So we build all sorts of different modules. We can build this module inside our digital manufacturing domain, but this Lego model don't necessarily limit it in our domain. We can also build this kind of common sense to like healthcare, biology, smart city, anywhere you think for a different world can be used for this Lego module. But now you might want to see some real examples, what we actually do with about these Lego models. So here I'm going to introduce you 2 examples of how we build a few models and how we do with them. The first of all is about a digital twin of an assembly line for a furniture company. A digital twin from the words is like a virtual reality to the real manufacturing system. So everything happened in the real world. The digital twin get what is really happening in the digital side, and then you can exchange data between these two. Digital twin is also an abstraction to the real system, because the real system's complexity also want to build the digital twin using multi-level abstraction. So now we form our tool set. we use a digital lens, which helps us zoom in and out between different levels of abstraction. So using that, we've been able to study how information, how data are actually flowing from the lower level to higher level and vice versa. And why we are studying that is because we want to know how different level of abstraction can actually work and how the system will behave. Sometimes we do experiment on the digital twin because it is really unpractical and expensive on the real system, so it saves time and effort doing it on digital twin. So we use synthetic data and the real industrial data to test different level of the abstraction and how information flows between them. And the use of this is we can find out, first of all, what kind of abstract level or best suited for a particular situation. And second, it helps us to install sensors where we don't need to, because we don't need to get data all over the place. Like when you install the CCTV, you don't want to put the camera everywhere. You want there into the critical position and be able to monitor the whole system. So the study helps us to decide what kind of sensor we should install, where should be, and how many of them. So this is one of the examples we use. And another module we build is for 3D printing. If we build a module which have a basic idea of how 3D printing works, we can use this module to help us decide what is the best optimal building orientation for given any object we want to the 3D printing to print. So they can decide the best option, the position to print, while we can also save printing time, save printing material, and also satisfy the functionality of the object. So we make all this kind of effort just trying to make the machine a little bit smarter. So we could, so they can be able to handle more complicated tasks. So then we can free from all this daunting task. We get to do more creative stuff using our limited brain power. But through the process of helping the machine become a little bit smarter, what is due to us? From my perspective, while we're making the machine handle this multi-level abstraction, we're also teaching ourselves how to abstract, how to think clearly, how to understand the world more clearly. This is also, it's about to say it makes us smarter, but it's also, I have to say, it makes us know how to think at a level. It makes the research a little bit easier because we're developing general method which applies not one single situation. We apply to all sorts of different situations. And that's the basic essence of what this research is about. It opens so many possibilities because you start to discover things are not previously related, they're actually related, and they're actually similar. So sometimes it gives us brain power to discover new methods and new technology for different problems. But I have to admit, I'm not a mathematician. I'm only using the fundamental level abstraction inside the world of category theory, because this kind of level already be sufficient enough to handle the complexity in our domain or the future complexity. But mathematicians actually are a step further ahead. They are studying the higher level of category theory. They're studying the infinite level of abstraction. The infinite level of abstraction actually is beyond my imagination. It appears to take you further and further away from the reality. But from a mathematician's point of view, they're getting closer and closer to the heart of the matter. But this also brings some new perspective about how we teach mathematics. The old traditional teaching, we teach mathematics as how the mathematics progressed. We teach small things and build up all the way ahead. But what about we give a God view of mathematics at the very beginning. This is like, you can see the Google. Google above the universe, you see what is the shape and what's the continent, the oceans, etc. You have the whole picture at first. And then you can step down to each different levels to see the view. After all, stepping down the stairs is much easier than climbing up. At last, I would like to thank one of my favorite books, Gödel, Escher, and Bach, written in 1970s by a cognitive scientist. He talks about how mathematics, art, and music have in common, and what is the essence of human intelligence and artificial intelligence. I also would like to thank one of my favorite mathematicians, Dr. Eugenia Tam. In her book, How to Bake Pie and the Joy of Abstraction, she really brings down the abstract math down to earth. She talks about how we can understand abstraction and abstract math in using our daily life. This gave me a lot of inspiration for this talk, and it is real intelligence to be able to simplify things than to complicate them. And on that note, thank you for listening.
I'm going to invite questions from our live stream audience shortly, but I wanted to ask a couple myself first, if that's okay.
Yeah, sure.
And the first one is really, it really was a fascinating talk, bringing so many different things into seeing, what underpins your research. What inspired you to work in this area of research, and have you always enjoyed maths and engineering?
In engineering, yes, because as I was a kid, I like to take apart of objects and then study how it works and then put them back together. So I have long interest about engineering per se. And so when I decided my major for my undergraduate, so my first choice was mechanical engineering in design. And my second choice was computer science, because I only get to know computer. I find it fascinating, but I don't have many chance to do that, to take apart a computer and study how it works. But math actually not that, because I think it's the way how it was taught. I found it at that level quite easy, not really challenging. I don't know why I'm studying the mathematics apart from passing the exam. But then after my undergraduate, because mechanical engineering in design, I get to operate some huge machinery like turning machine and huge forging machine. They're quite scary, actually. I don't think they are the kind of my cup of tea. So then when I decided my master, I thought, okay, let's try some precision stuff. So that's why I went to the precision technology to pursue my master and then PhD afterwards. And then I got lucky because then I got to learn more things about computer science and how they can apply it in engineering. And along the way, I found math is really useful and to help me build towards my research. So then, but it's only until recently I discovered how abstract math can help with me. I really them to rethink about mathematics and discover the beauty of that. So
I think that's really interesting, and I hear that a lot from people, that they feel maths is just something to pass as an exam, but then later on in life really see the value of how it applies to so many different situations. So
yes,
I think you're not alone in that experience. That's great. So Ada Lovelace Day, and you mentioned her in your talk, started to highlight a woman who had a huge influence on mathematics and computer science. How important has it been for you to have women role models in the area of research that you look at?
Yeah, but when I decide what I'm gonna do for engineering, I actually just follow my interests. We don't have many women role models to look up to. What a shame. But it's only until my master research I got to pick the best female professor in this area. So I was really lucky. So I chose the right supervisor, which helps me a lot. And throughout the journey, I got to know so many brilliant ideas in female mathematicians, female computer scientists, female researchers in the engineering domain. I think they are they are on their way of fascinating and how they get to reach to the success. It is important and has the role model, so you get to know we can be successful. But also at the same time, I feel using role model not just sufficient. Breaking the stereotype about mathematics and engineering in general or manufacturing is more important, because we got a mental image of how the engineer will be in a traditional sense. Because when I first came to UK, an old gentleman asked me what I'm studying. I said mechanical engineering, and his reply was, "You don't look like an engineer." I was a bit speechless. What an engineer should be like. Holding up a spanner and operating a huge machine, wearing the helmet. That's a typical stereotype. We should, because now manufacturing actually changed a lot. It's digitalized. It's going to be even more different in the future. We're gonna have a less and less role to actually operate the machine, because the machine can do them by themselves. We're going to have more and more creative opportunities, creative job titles. So we don't have this mental image of how engineering should be. You can wear a pajama and then control it using an iPad at home. Yeah.
That's a really good point. Thank you. I'm just going to open it up to see if we've got any questions from the live stream. So.
We do, yes. So Andrew would like to ask, do you think this type of abstraction is more easy to define and validate for computer science applications rather than physical, sort of mechanical and electrical ones?
Right, so that question was, I'll try and summarise, is abstraction more simple to apply to computer science applications rather than the electrical and mechanical engineering situations?
From my point of view, or from some category theorist point of view, abstract math can apply to all sorts of things, even our simple life. It might appear to apply to more digital abstract world, like computer science or mathematics. I think that's a still stereotype. I'm sorry I have to say that. But you can still say everything you want, simplify things, you want to make it clear from all these complicated things. Abstract math is a way to go. Yeah.
Thank you.
And also, what's the most rewarding thing about your work?
So the next question, that's a really tricky one, I think. What's the most rewarding thing about your work?
It's really difficult to pick out the most. I think there are a couple of rewarding things. First of all, I think from my own perspective as a person, and it makes myself thinking clear. I think that's for myself, that's the most rewarding thing, is because I'm not quite good at thinking to start with. And getting to know the abstract math actually developed my philosophical research, helped my journey of research, helped my think clearly. And as my research work, I think sometimes it's really rewarding when I speak about this and then shout out about how important abstract math is in our engineering domain. And some people approached me and want to work with me because they think this method can actually help them. So we have the one with the digital twin example I showed in the earlier talk actually was developed like that. And also because sometimes it's lonely because not many people are actually using this method. And so we also get to, there's a group coming from United States, and then they also using category theory in their research. So we kind of like click on and say, oh, right. So it's really rewarding to say somebody else is doing that. So we are not alone, yeah.
Great. Thank you. So I've got another question. You seem to really simplify mathematics, and maths to many people seems really hard. So what would you say to people who think maths is too difficult, too challenging?
Actually, I still think so many of part of maths are really hard for myself. Yeah, I'm just really starting to revisit mathematics. So first of all, we need to think the part you're actually studying, whether west of studying. Sorry, I have to say that because some of the mathematics is actually a little bit redundant in this modern world. And if the things you are studying, you think it's really worth of doing that, don't force yourself doing it. I think force yourself doing it will kill all the fun. I think you can work out by from different angles, how to make it tiny little bit simpler or a little bit fun. There were so many. The way how math was taught, because so often they use complicated mathematical examples to illustrate a complicated mathematical theory, so which it makes it even more complicated. But we can use our normal life examples, daily life, which you can understand. Trying to find those resources. There are plenty of learning material, and you can ask mathematicians about that because they are so open, they're so willing to share what they think about. And read some books. How to Bake Pie is one of them. Yeah, it's really simplified and then just changed my world. Yeah.
Okay. I'm not sure if you've got any further questions from the live stream. We do. Oh, that's interesting. How would you get, I suppose what the question's asking is, how would you sort of download the data from a professional baker's head to input into these sort of models to create the perfect pie?
That's a great question, because that is the difficulty about. Originally, we want the machine to learn this stuff, so we don't need to build this Lego for them. But machines are not that intelligent yet. They can't handle. They don't know how to abstract to start with. But they are working on that. So we have to build that for them. So that's the real hard job. So either we teach the baker to use her, because they will know the own knowledge and they will know how to build a module. But sometimes it's really hard to let them to do it on a digital world, on an abstract world. So sometimes we have to using the expert and ask them questions to build that model for them. But that actually is the most challenging part from my point of view. And the best way of doing that is the machine can learn to do it. They just watch video and then watch how a baker bake a pie, and then they know how to do it. But we're not that level yet. So we have to go through this converting the human knowledge into the Lego module. So this is a hard work.
Great.
Do you find that maths puts people off when you're talking to people? What can we do to help society stop being put off by maths?
Okay, so that's a really good question. Do you find people switch off when you're talking about maths, and what can we do to prevent society or get society talking about maths?
I think it should be a group of effort for all of us, or for mathematicians, for the math educations. They should use more life-related or simple examples to illustrate. Don't start with the difficult concept first. Start using examples. I think Dr. Eugenia Tan, she is the expert of doing that. She really brings the category theory down to earth and using this daily life example, and also inspired a lot of mathematicians as well, and lots of appreciation. I think reading some of the books and then listen to some of the talks, which can actually simplify math to start with. We can't expecting a huge change in a short time, but doing things step by step, a bit little. Yeah, start to think about how you can simplify from yourself.
And it is just such a fascinating topic, isn't it? That there's so much diversity in mathematics and engineering and science, that there's something for everybody, really, isn't there?
Yes, yeah. Actually, I was thinking my vision for this, how my work are gonna help with that is if everybody are able to understand abstract math, and even for a primary school student and pupil, they can understand the abstraction. Maybe in the future, they can understand different disciplines. They can find a similarity between different the disciplines, though they know. So it's much easier to have more transdisciplinary areas, so they know all different things at one go. So they can, so this gives them a huge power, and then they can tackle like grand challenge like climate change or etc. Yeah. That's a grand vision, but maybe not in my generation, I would say.
Brilliant. If there's no further questions, we do have one final one.
Another one's just come in. What advice would you give to someone wanting to get into this area?
What advice would you give to someone wanting to get into this area?
Yeah, you see, you just said it's a quite diverse area. You have to find out which particular point you are more interested in. If you are more interested in about the math, and you get to know this area a little bit deeper, and talk to people who is in this area, and then also for computer science and engineering or manufacturing domain. And yeah, just think about how you're gonna find your interest first, to know the area first. Yeah, talk to experts or talk to people what they think about the area of interest in the area of research.
And
first.
just find something that sparks your
find your
passion.
sparks. Yeah. Explore the different resources.
Great, thank you.
And another one, do you think this process of deconstruction demystifies many areas which are considered artistic processes?
Right, so that's a question. I'm going to try and capture that. Do you think that, I'm sorry, I'm going to ask that to be repeated.
Do you think that this process of deconstruction demystifies areas which are considered artistic processes?
Right, so do you think that this method of deconstruction demystifies areas of artistic processes? That was a question sent to challenge us both. Over to you.
I think this is a great question because, you know, Dr. Eugenia Teng, she's not just a mathematician. She teaches abstract math category theory to art students. So this is a great example how learning abstract math can help the art student develop better at art, in my sense. And she has really answered that question for me already. Yeah. You can spark the great idea and then create new things and generate all sorts of abstract geometry or abstract art or all sorts of art. Yeah, from a non-artist point of view.
Excellent. Well, my final question had been asked earlier, so I'm going to end on this one, which is, what is your actual favourite pie filling?
I think I'm going to choose shepherd pie.
Oh, shepherd's pie.
Yeah.
Very good. I think mine would be cherry. Brilliant. So thank you ever so much for the talk today and answering all those questions. It's been really fascinating. I'd also like to thank Carolyn Bishop, who you saw popping on with the stalls for us. She's been instrumental in developing this series of lectures, and also thank you to the entire production team.